Hello everyone, welcome back to Mind Over Math. This today is going to be on rational equations, which is a hyperbola that has a vertical and horizontal asymptote. This presentation is on rational equations which make the shape the hyperbola. The first and the simplest rational equation is actually called a parent function, and that is f of x equals 1 over x. And if we just can start this by using the table of values, and if we plug in the negative 10 into x, we will get negative 1/10, which would be 0.1. And if we plug in negative 1, we get negative 1. So let's see here. This would be right here, right here. And then 0.1 would actually be 1 over 0.1. And if we move both decimal places over one place, we would get 10 over 1. So that means, and this is negative because this was negative. So this would be, down here below and out of the line of the picture. So this side would look something like that. And then at 0, if you realize 1 over 0 is an undefined number, undefined, and that means this is a vertical asymptote. So a vertical asymptote is a hole in the graph at x equals 0. Nothing's there. Nothing will ever be there. A vertical asymptote is just that. It's a hole in the graph. Then we go to the right of the y-axis and plug in 0.1, and again we get 10, which means that's up here. That would be over here. And then we plug in 10, and we get 1 over 10 is 0.1. So that would be out here. And then if we plugged in a 1, we would get a point right there. So that's the hyperbola. This is actually a first third quadrant hyperbola. And there's two important parts to the hyperbola. The first part we've already talked about, and that's right here. That is the vertical asymptote. Typically it's at x equals 0, but in our application it's going to be whatever's in the denominator is equal to 0. So in this case x equals 0. The horizontal asymptote is also there, and that is typically y equals 0, or it's equal to y equals the lead terms in the fraction. So typically it's y equals 0 unless we have a reason to believe otherwise. So the horizontal asymptote would be, in this case, right along the x-axis. Now that's the default horizontal asymptote. It will move when there is a need to, and we'll know that when the lead term equals y is different than 0. So let's see where that takes us. In this example, I want to remind you over here on the right, just a little bit of memory work here. Nod, if you can nod right now, that means numerator over denominator. Just a little reminder on vocabulary numerator over denominator. And of course that's a very important vocabulary to remember those because we need those to graph this. So basically a rational equation has x in the denominator. That's what makes it a rational equation. The root word of rational is ratio. The root word ratio means fraction, and you'll notice I have a fraction with an x in the denominator. So in this one we want to talk again about the vertical asymptote. First thing, vertical asymptote, which in this case is the denominator set equal to 0. So we're going to take x minus 3 and set it equal to 0. So x equals 3 is the vertical asymptote. So over here at x equals 3, we're going to put our vertical asymptote. Second, we go to horizontal asymptote, and the horizontal asymptote is the lead terms. And the two lead terms here happen to be 2x over x. They are the lead terms because they have a variable and it's the highest exponent in each line. So down here you see the two lead terms. You set them equal to y. This will give us a horizontal asymptote. Now this fraction will reduce to y equals 2. So the horizontal asymptote is at y equals 2. So we'll go right along this y equals 2 line. These are the two most important lines of the graph. They define the vertical and the horizontal axis. It's actually shifted. The x-axis has shifted up 2. The y-axis has shifted right 3. The last two things we want to do are locate the x-intercept. It's actually a really nice way of happening. The numerator, as it turns out, when you set it equal to 0, will give you the x-intercepts. So this gives me x, do this a little faster, x equals 5 over 2, which is 2.5. So I'm going to go over to x equals 2.5, which is right there. That is the x-intercept. The next thing I'm going to find is the y-intercept. And the y-intercept comes from the last terms. The two last terms are -5 over -3, and that reduces to a positive 1 and 2/3. So up here I go up to 1 and 2/3 on the y-axis. That tells me this hyperbola is going down just about like this, goes down forever. And then I need to pick one point to the right of the vertical asymptote, so I'm going to take the point 4. And I want to see where that is, so I'm going to plug in x equals 4. And I'm just going to plug it in here to the original equation. Plug and chug. So I get 8 on the top minus 5 is 3 over 1. So at 4, y is 3, which puts a point right there. That gives me the idea that the right wing of this hyperbola, we have left wing and right wing, is in first quadrant, and we already showed that the left wing is in third quadrant. Now you'll notice these quadrants have actually been a shift from the original first quadrant, 3 to the right. The x-axis has shifted up 2, up vertically 2. So we can do any graph of a hyperbola by understanding that the numerator tells us one thing, the x-intercepts. The denominator tells us only the vertical asymptote. The lead terms tell us an important part of the hyperbola, which is the horizontal asymptote. And the last terms, which is the constants, show us the y-intercept. So with those points, and then I had to find one more point over here at 4, I could determine that the shape of this hyperbola was a first and third quadrant shape. So I hope this helps you. This is part 1. Part 2 will follow on rational equations, the hyperbola. Thank you.
In the upper right hand corner, make sure you subscribe. In the upper left hand corner, make sure you check out other videos. Likes are below and make comments on topics you need.